Did you know that deep learning is a key reason why you can ask your phone natural language questions, or for it to translate languages on the fly? This fascinating field, a subset of machine learning, is shaping the world around us in ways we often don't even realize. It's the engine powering your voice-activated virtual assistant, the technology behind your social media feeds' eerily accurate recommendations, and even the magic that enables self-driving cars. Deep learning is embedded in the fabric of our everyday lives, silently working in the background to make our interactions with technology more intuitive, seamless, and efficient. At the heart of deep learning lies a concept called artificial neural networks, inspired by the human brain itself. These networks are designed to interpret sensory data, recognize patterns, and make decisions, much like our own neural networks do. So now that we have a basic understanding of what deep learning is and its relevance, let's delve deeper into how it works. Deep learning might sound complex, but it's not as complicated as you might think. Picture this. It's like teaching a toddler how to walk. Initially, the child stumbles, falls, but each time they get back up, they improve. They learn from each misstep, and slowly but surely they start walking. This is precisely how deep learning works. So, what's happening here? Deep learning is a subset of machine learning, which is essentially a neural network with 3 or more layers. These layers work together to produce a prediction or decision. In the context of our toddler, think of these layers as different stages of learning to walk: crawling, toddling, and finally walking independently. Now let's talk about training models. Imagine you're teaching a dog to fetch. You show it how to do it, reward it when it does it right, and correct it when it doesn't. That's training in a nutshell. In the realm of deep learning, we feed a model with data, allow it to make predictions, and then correct it when it's wrong. Slowly, the model learns to make accurate predictions. But how does the model learn from its errors? Picture this. You're learning to play a new video game. Each time you lose a life, you figure out what not to do the next time. This trial and error process is the essence of learning from errors. In deep learning, this is done through a process called backpropagation. When the model makes a mistake, it goes back, adjusts its calculations, and tries again, improving over each iteration. So if you think about it, deep learning is not that different from how we humans learn. It's all about learning from experience, understanding the consequences of our actions, and constantly striving to do better. It's about making mistakes, learning from them, and improving over time. So, essentially, deep learning involves training a machine to learn from its mistakes and improve over time, much like we humans do. But how does a machine learn from its mistakes? Let's dive into the nuts and bolts. At the heart of deep learning, we find a fascinating concept known as artificial neural networks. These networks, as you may have guessed, draw their inspiration from our own biological neural networks, the intricate electric web of neurons that make up our brains. Now let's not get lost in the complexities. Imagine a neural network as a team of players, each with a specific role. These players, or nodes as we call them, are organized into layers. At one end we have the input layer, which receives all the raw data. This is where our game begins. On the other end we have the output layer, the goalpost where we want our data to score. Between these two, we have what we call hidden layers, where the real magic happens. Each node in these layers carries a weight, much like a player's individual skill set. The higher the weight, the more important that node's role in the final decision. But it's not just the weights that matter. We also have something called biases. Think of these as the coach's instructions to the team. They help tweak the game strategy, ensuring the output is as accurate as possible. Here's where it gets interesting. During the game, as the data moves from node to node, from layer to layer, the weights and biases adjust based on the results. If the output is a miss, the network learns from the mistake, adjusting the weights and biases to improve its accuracy next time around. This is the essence of learning in deep learning, the machine's ability to learn from its mistakes, to refine its strategy, and to continuously improve its performance. So in essence, an artificial neural network is a computing system somewhat inspired by the human brain, and it's this system that enables deep learning. While the basics are fascinating, deep learning has far more to offer. It's time to explore some advanced concepts. Let's start with convolutional neural networks, or CNNs. Now don't let the name intimidate you. These are simply a kind of neural network that excel in processing grid-like data. Think images, which are essentially grids of pixels, each with their own values. CNNs are designed to automatically and adaptively learn spatial hierarchies of features, which makes them great at recognizing patterns in images, like telling a cat from a dog, or a stop sign from a yield sign. But what if we need to recognize speech or text? Well, that's where recurrent neural networks, or RNNs, come into play. These networks have memory. They can process sequences of inputs, remembering what they've seen so far and using that information to understand context. This makes them perfect for tasks like speech recognition or natural language processing. For instance, when you ask your smartphone to set an alarm, an RNN is likely at work understanding your command. Now let's move on to something that's been making waves in the tech world: transformers. No, not the robots in disguise, but the model architecture that has revolutionized natural language processing. Transformers, introduced in the paper "Attention is All You Need," have the ability to pay attention to different parts of the input data, giving more importance to the relevant parts and less to the irrelevant ones. This has made them incredibly effective in tasks like translation, summarization, and even generating human-like text. But it's not just about recognizing images or understanding speech. These advanced concepts are being used to push the boundaries of what machines can learn and do. For instance, reinforcement learning, a type of machine learning where an agent learns to make decisions by interacting with an environment, has been used to create programs that can play complex games like chess and Go, often outperforming human champions. And then there's generative adversarial networks, or GANs. These are a class of artificial intelligence algorithms used in unsupervised machine learning, where two neural networks contest with each other in a game. One network generates candidates while the other evaluates them. The result? Machines that can generate shockingly realistic images, music, and even text. In essence, the advanced concepts in deep learning are not just about making machines smarter, but also about expanding the scope of tasks they can handle. From recognizing patterns in complex data to understanding and generating human-like text, to making decisions based on learned experiences, these concepts are pushing the boundaries of machine learning. And the best part? We're just scratching the surface. As research continues and technology evolves, we can expect to see even more fascinating developments in the field of deep learning. These advanced concepts are pushing the boundaries of machine learning and opening up incredible possibilities. Deep learning is not just a buzzword, it's a revolutionary technology shaping our world and future. We started our journey exploring this technology by decoding the basic concepts. We learned that deep learning is a subset of machine learning, and it's all about neural networks. These networks mimic the human brain's functioning, making machines capable of learning from the data they're fed. We understood that the more layers in a neural network, the deeper the learning and the more complex problems it can solve. Moving forward, we delved into the core elements of deep learning. We discovered that it's not magic but mathematics and algorithms that drive this technology. We talked about data, models, loss functions, and optimization algorithms, all acting as cogs in the deep learning machine. We then ventured into advanced concepts, understanding convolutional neural networks that power image recognition, recurrent neural networks for language processing, and generative adversarial networks that are changing the game in the field of art and design. We also touched on the challenges that come with deep learning, such as overfitting, underfitting, and the need for vast amounts of data and computing power. But the journey doesn't end here. The potential of deep learning is immense. From self-driving cars to virtual assistants, and from early disease detection to climate change modeling, deep learning is making its presence felt across industries. As technology evolves, we can expect more sophisticated and efficient deep learning models. Quantum computing might significantly reduce the time taken for complex computations. Transfer learning could allow us to train models with less data, and explainable AI might solve the black box problem, making AI more transparent and trustworthy. The future of deep learning is promising and exciting. It's no longer confined to research labs and sci-fi movies, it's here, and it's changing the way we live and work. So next time when you ask your phone a question, remember, there's a lot of deep learning going on behind the scenes.